Welcome to solverfy.
In this problem, we have, let's see here, this one. We have a block suspended from a couple springs and a damper, and we have this block, and then this plate here is being accelerated up and down. This problem actually is kind of, I think, probably a little harder than they anticipated it to be, because it turns out if you draw free body diagrams and go through everything, the excitation over here is not just the equivalent stiffness times the base motion. You also have the equivalent damping, or the damping coefficient times the time derivative of that motion, because you're causing excitation through the damper also, as well as through the springs. So this complicates things quite a bit, and I'm not sure if this is what they had in mind, but this is how they drew it. They could have put the damper, say, underneath the block and connected it to ground, and then had the springs here being excited, and that would have gotten rid of this term. But that's not what they did. So we'll analyze what they have. So we've given all this information about the system. We can figure out the natural frequency is about 16 radians per second. The amplitude of the excitation is 3/4 of a foot, and the frequency is what we're looking for. So we can find, this is our excitation, and we can figure that out by substituting into here and then taking the time derivative and substituting in there. And what we get is two terms, one with a cosine, one with a sine. We can then use trig identities to combine these into an amplitude and a phase. And so then the amplitude is going to be the square root of this squared plus this squared, and then the phase will be, an inverse tangent of something. But in this case, we're not really worried about the phase. So we can write the forcing amplitude in this way, because there's a delta naught square term in each of these, and we can pull it outside the square root. And so this is our the amplitude of our excitation. We can also figure out the damping ratio from the information we were given, and that is 0.501. So actually this is quite a bit of damping. Now we can find the amplitude. The amplitude of the response is the amplitude of the excitation divided by the equivalent stiffness, which is 2k in this case, then all divided by this square root term, which is 1 minus r squared squared plus 2 zeta r squared. And so we see this again. And we're told that that is half a foot. The amplitude of the response is half a foot, and we were looking for what the excitation frequency would be. And so again, we can look at either plus or minus. And in the case where we take plus, we get a excitation frequency of 30.5 radians per second. Now, if we take the minus sign, we get no answer. And why that is because in this case we have this system where we start here at some what we call kind of a DC offset, or a static displacement. Come up here, hit our resonance, and then come back down, and then eventually decay down here to 0 again. But what we're looking for is an amplitude over here, down here. So there's only one value. There's not one on each side. If we were looking for a larger amplitude, we'd find two values, but now we only find one. And we can see that this is above the natural frequency, and so that was what we'd expect from this curve here. Since we're down here, we'd expect to be out here above the natural frequency. And so that's what we get for our excitation frequency if the response amplitude is half a foot.